Probably is a downfall parody.
And where's there you go.
Thank you. Okay, thank you for coming. We thought we should have a very introductory part of the tutorial because it was unclear how familiar everyone would be with PETSc. So the idea of this part is to be introductory, but also to try to communicate the overarching vision or the design goals and stuff, because that kind of thing is very rarely in the documentation, but it's probably the most valuable thing for helping you understand how to use the package. If you can understand how the people who made it are thinking, it helps you to find the information on your own or add things to it in the same style and stuff like that, I find. So I want to explain what we are trying to do. So this is, I think, for me, the most important thing. This is what I think about scientific software. Papers that are published that say this algorithm runs this fast, that don't allow you to run the same code, are worthless. They are worthless papers. And it's worthwhile to prove that stuff converges. It's worthwhile to prove that it's robust to certain perturbations. But if you want to know how things run, or if you want to understand how interfaces are constructed, there's no substitute for being able to run it yourself. So the original motivation for PETSc is to be able to do this for certain classes of linear solvers. And over time, we added more linear solvers, nonlinear solvers, optimization solvers, time-stepping solvers. But I think the motivation is the same. It is to enable the average computational scientist to run not only their own algorithms, but the algorithms of all the other yahoos that are publishing in the field, so they can directly compare with this stuff rather than talking past each other when you write papers. So these are some of the people in the project. Younger people have better pictures, obviously. And just to give you an idea of how old it is, some of us are very old at the top and have been doing a lot of work. So I used to show this slide, and it used to even end about here. But now what you can see is there are very many people that are not old that are developing. And this is where some of the most exciting new stuff comes from in the package. So I had to make a new slide. And so that's why it's a very exciting moment to start contributing your code to PETSc. You can be with all these people working very hard instead of these people with tenure not working as hard. So another goal of this kind of talk is that you can ask questions, because none of it is that serious, and it's not laser focused like some of the later stuff on exactly a particular thing. So feel free to ask the kind of question like, can you do this? Or has anyone ever implemented this kind of algorithm, and how would they do it? This is a perfectly good venue for saying stuff like that. If you don't want to say it to everyone, you can mail it here, and someone will probably answer you before I finish talking. It's very good response time. So again, you can ask questions. And so the kind of stuff I was thinking about talking about, I'll do an intro which says things about the package and how it was created. And then maybe I'll try to show an example of how you would integrate PETSc into a code that's already running. In some sense, new codes are the best case scenario for us, because from the ground up, you do what we want you to do and everything is great. But that's almost never what happens. What happens is you have a beautiful existing code that you love, but if just did one more thing, you would be happy. And so you don't want us to break absolutely anything that you do now, but you'd like it to be able to do something that we can do. And so that's what I want to try to show an example of. And then at the end, I probably won't have time for everything, but I'll ask you what you're most interested in. I have examples of doing stuff that's a little bit higher level, like how do you handle meshes? How do you handle solvers that are actually ones you want to use instead of toy demonstrations for class? But first, I just want to go over, basic stuff. So PETSc is about doing experiments. In this way, it's a little bit different, I think, than something like Abacus or Fluent, where they say there's a set of problems that we deal with, but if your problem fits in this class, then you just push the button. You choose from a drop-down list of things you can change, and it just runs, and we guarantee it'll work, or you pay us a lot of money for consulting fees, and it will work. But PETSc is more a set of tools. It is intended that you read some papers or talk to people, and they tell you, oh, you really must do this. It's the best way to do it. And in PETSc, it should be easy to build that. It might not exist at the time, but you should be able to put it together with not so much effort. We're interested in things like being able to put together optimal solvers, being able to closely couple discretizations in solvers so you get the thing you want. Obviously, we leverage a lot of things too, which I'll talk about, but we use a lot of other packages because that's the philosophy. Use the best library for the thing that you're doing. We don't have a not invented here problem, I don't think. So this is a Barry quote, which I really like, because the overselling that happens in PDEs is terrible. So we have dumped decades of work and probably hundreds of millions of dollars in funding, and it's still not very easy, but it is doable. And so we're not trying to make it easy so much as we're trying to make it doable to do anything you feel like doing. And then I also like, the slides are up, so you don't have to read it all, but the thing that's cool about this, so Bill was giving an interview and said what I think is a very succinct way of putting our approach to design, which is a lot of people think about designing, I really would like to vectorize, or I have to take advantage of multi-core. But that's putting the cart before the horse. That would be like building your house where you're like, this brick goes here, and then I will put another brick exactly even with it here. You will never get your house built. And so what we tend to do is do the top level design first, and the goal there is not to screw up any opportunities for optimization rather than to design with the optimization in mind at first, because probably your optimization target is moving. So listening to me is okay, but it's better if you can find out all this stuff by yourself, because it makes, I think, a bigger impression. So all the documentation is at the website, and these are all links. So when you get the slides, when they get posted, you can click on them, because I hate when it talks about things in slides and it doesn't have a direct link to it. So I think I have links for everything. There's a manual. There's hundreds of examples. There's manual pages for all routines. And I would mention my favorite thing about the documentation that just happened is Patrick wrote a nice thing where we have the top-level API and a web page, but on the web pages are links to every implementation of that particular API function for concrete types. So it's easy to see now what actual computation goes with the high-level interface functions. Because, for instance, in a matrix, there might be 20 implementations, AIJ, block AIJ, LPAC, all, jagged diagonal. And so you can click and you can go straight to each one of the implementations and see what's going on. And we have bindings to bunches of languages. I've never used the Julia bindings, but if someone did, that would be cool. So it can run anywhere. I can't think of a computing platform where it does not run. runs on the phones, it runs on Raspberry Pi, runs on the big machines. So if there's something that it doesn't run on that you would like it to, definitely ask. And I guess we should acknowledge the funding sources always. So we get funded by the Department of Energy mainly, but also we have significant funding from the National Science Foundation, and we were funded by Intel. And in fact, are the funders for the conference?
EPSC and the Quantitative Sciences Research Institute, Edinburgh.
Very nice. And so Intel also gave some money for student travel. So I just want to give examples. This is, of course, not exhaustive, but I want to try to give you ideas about how other people have used it so that you might see opportunities for yourself. So there have been many earth science packages built on top of PETSc, where PETSc is sort of at the lower level doing things like solving. Pilot and Solvis both use the mesh handling capabilities too. Underworld, which does simulation of the mantle and crusts, it uses the solvers right now, but may start using the mesh things. And then Terra Firma is a Magma Dynamics two-phase flow thing. And multi-physics packages like Moose or Grins, both of which are built on libmesh, use PETSc at the lowest level for solves too. So you can see that one avenue would be, oh, I have a larger package. I can use some of the functionality for solving linear or nonlinear systems or time-stepping problems. In CFD, things like IBAMR or Immerse Boundary AMR or Fluidity do that too, or these fusion packages. But you can also do just algorithm development, and I would say it's a pretty good platform for algorithm development for two reasons. One is that the interfaces are fairly clean and composable, so that it's fairly simple to take parts from other domains and reuse them in your algorithm development. So we get a lot of leverage out of that, and I'll show you examples, for instance, of complicated linear solvers built out of simple parts, or also nonlinear solvers. But another reason is that once you do your development, you have a built-in audience for it that's rather automatic. So I could use the example of Peter's code StrumPack that does it's a hierarchical factorization of low-rank matrices, right? And they did the development of this package, but it plugs in so that it can be used on all these problems that they can automatically test, and there's a built-in user community. So there's a lot of leverage there. And I guess HPDMM, same thing, it just released the PETSc interface. I went online and checked, so I checked it in a little while ago. So it now works. And then there are libraries, not applications, but libraries intended to be used underneath other applications, and PETSc is underneath that library. So a good example for this week is FireDrake, which uses it in exactly this way and uses all of the cool mesh stuff. Yay! But libmesh does the same thing. Deal2 does the same thing. Slepsy does the same thing. Permon does the same thing, all of which are intended to be library structured in very much the same way that PETSc is library structured, rather than like an application. This is just, can it run big problems? The answer is obviously yes. These numbers are constantly out of date, so Jed says, why even put up numbers? But I think, especially when you're giving talks to program officers and stuff, they want to see numbers like this that prove that it will work. But I'll just show examples of things that I thought were cool, because sometimes it's hard to see whether what you're being shown is an elaborate string of demos that are very fragile and hard to generalize, or whether you can take this technology and put it in a real code that can solve practical, complicated problems rather than toys that I would normally show you. So these are practical, complicated problems that people write science papers about. So Pylith is a thing that does crustal deformation. Either dynamic is when you get an earthquake rupture, or quasi-static when you have the relaxation of stress after an event. So it's nonlinear viscoplastic, it can do finite deformations, and you can actually put constitutive models on the fault. So you can do sophisticated things like rate and state friction and healing and all that stuff. So you can get nonlinear dynamics that are complex. It can handle 1D, 2D, and 3D problems, and it can couple 2D and 3D and 1D problems together in a pretty flexible way. And I think that is the kind of defining characteristic. And the thing that I am proud of is that the code inside that does the assembly of operators and residuals and Jacobians is mesh and dimension independent. So there is one routine that does it, but it can, by changing the input, you can get all of those different problems together. And so that was one of the big goals that we had. So this is the test case, but you can imagine if you want to couple different, sub-manifold problems together with manifold problems, or you have a multi-physics problem that has a lot of different things to be assembled, that we might be capable of doing that. So showing off meshes. This is in Magma Dynamics. It's a good example of sort of traditional multi-physics where I have two-phase flow, so I have an incompressible fluid in a deforming solid matrix. So the solvers are fairly sophisticated, and we can put those together easily. And so this is Rich Katz looking at the porosity beneath the mid-ocean ridge. And he doesn't do full-time code development. He is a scientist, but he was able to put this together with modest amount of work and have it produce real physics results. This is channeling. This is just the sparks kind of thing with an impermeable layer, and then you get channels into permeable stuff. Oh, and so this is another example where it's a somewhat complicated solver setup, because this is a variational fracture model. So fracture, I think until maybe 10 years ago, had primarily been done by things like conforming meshes or XFEM, and most of that introduces geometric complexity. So the variational form was an attempt to trade the geometric complexity for analytic complexity, so the model is a little bit more sophisticated. So you trade a simple linear system for now an optimization problem, and you have to prove that it converges, so it actually gamma converges, so there's a little bit more sophisticated analysis. But the other thing is the solver now has to be an optimization solver. And it was pretty easy for Blaze to bring in the optimization part of PETSc, the tau solvers, so he could do, for instance, L1 penalties. And L1 penalties are the only appropriate penalties. So you can solve this as an unconstrained problem with quadratic, but the problem with that is that cracks talk to each other over any distance. And so you don't want this where they sort of head towards each other because there's a finite distance in real materials, and L1 penalties give you the correct behavior. And for that, you need a more sophisticated solver. Tau can do that. So for instance, now you could do arbitrary crack geometries. So for instance, you can do 3D cracks. So these are thermal cracks in an engine, and you can see they intersect and they have complicated topology. I won't even go over that. And we could do, so Dave and I were able to build a gravitational solver with the FMM, so completely different algorithm than we're used to, but we still had the pieces that were able to do easy parallelization, easy load balance, and easy assembly. And so we used those with a fairly naive FMM implementation that I had, and we're able to get good results for some of these gravity problems that you see in mountain building. Oh, and this is cool PD constrained optimization from Dave Fuentes. This is actually a dog with cancer, and they're trying to operate thermally with it. So they take a laser and burn it out. So he phrases it as a PD constraint optimization problem. So that was him and Tinsley Oden when he was a student at ISIS. And these are hard, nonlinear PD constrained problems that are multi-physics. So lots of different things are going on here. Elasticity, you got the thermal, you got the control. So it's a big solver problem to deal with. Okay, so those are some of the kinds of things that have been used for. So hopefully I've convinced you that this might be applicable to problems that you're interested in. So now I just want to talk about the very low-level nuts and bolts of how do I get it so you can quickly, so it should be possible for you to download it and build it in the time that I am speaking. And the reason is that, again, you should not believe anything that I tell you. You should only believe what you can do yourself on the laptop in front of you. So I just want to try to go over how easy it should be. So suppose you have Windows. It could still be easy for you. So what do you need to do? You need to have either you need Cygwin, or you can do this on the Bash shell in Windows 10. Okay? So the Bash shell in Windows 10, you just do the Linux process, and I've got it to work. I know Satish has got it to work. It shouldn't be any different for you guys. If you don't have Windows 10, then I would recommend Cygwin because we need Python and we need make and we need build utils. Now, you could possibly get away with like active state Python for Windows, but you'd still need make clones, and I think we use sed sometimes. So you'd have to find a way to get those outside of Cygwin. Once the libraries are built, we have no dependence on Cygwin. So you can build with the MS compilers, you can make DLLs, it'll all work the normal way. You can do your compilations under Visual Studio, no problem. It's just we need some of the build tools right now. So how do you get it? I think everyone should use the repository, will be my argument. However, people allergic to repositories, there are still tarballs at the download site, and there's a Debian package. These are all links, so anything magenta is a link again. And I guess you can post the slides right now if you want to download them and click links, right? Because you have the PDF. I sent it to you.
Yep. Where am I going to post it?
Post it to EasyChair. Doesn't have.
Oh, yeah, that's true.
It's the 21st century, right? So, okay, here's my argument. Why should everyone use the repository? Because there's nothing that you can do with downloading tarballs that can't be done with the repository. How does our tarball get built? Automatically from the tagged version in the repository. So if you want exactly the tarball, you can just check out the tagged version and have it build the stuff that goes into the tarball. For instance, all the documentation and stuff like that. It's easy to get hot fixes. You just pull the mate branch and get all the fixes that we're constantly making. It's easy to test the new version that will be coming out by switching to the master branch, see if your code breaks or your code's fine, and then roll back by just checking out mate again. So it makes it effortless, I think, to move between versions and to upgrade your code as things change, because we constantly upgrade. I think that's the only viable way to do it scientifically. Getting stuck in a particular version ultimately redounds against you, right? So you'll notice that we only maintain the interface for one version of every package that we depend on, and it's the latest version. And as soon as they release a new version, we throw away the old support and we support the latest version. So everything is continuous for us, and it's the only way we found you can have a small team and support things. Also, the advantage of using the repository is if you ask us to fix something, it can happen in an hour for you. And then you have it and it's done, rather than you waiting for us to somehow make a tarball and post it. So how do you do it with the repository? You can clone. Now, by default, the clone will put you in the master branch. That is, so the PETSc organization, I guess I can say a little bit about it. I wasn't going to go in too much depth. We have a maintenance branch, which is the release and fixes. We have a master branch, which is active development, but master is stable in the sense that you will never clone master and it will be broken. Never. Never, ever. It doesn't happen anymore. And so I would recommend using master. I think that's the right way to develop. If you have a library that has to depend on us, maint is probably right. But if you're doing your own development, master is better because you will get new stuff immediately. However, you can check out any release. So here, oh, why does it say 3.7.5? I changed my slide. This is old. Oh well, I did change it. Oh well, that's terrible. I redid that. It's 3.9.2. That's the latest release. I must have not given David the right PDF. So you can check that out, or you can unpack the tarball. After unpacking, you have to configure. What does configure do? Configure runs a series of tests on your machine to see what you have. Why do we do this? Because people usually lie when they tell you what their system is like, and that is the cause of innumerable configuration failures and later mails to PETSc main. So the style of package.conf or package config that where you tell me what's going on does not really work. I think people who believe in that also believe in fairies. What you need to do is you take the user input and everything has to be tested, and then we write out instructions for doing the build. So configure does things like test the location of headers, test the location of libraries, test that certain symbols exist, test that certain packages are there. And in fact, what we have is the ability to download and build packages for you. That's probably the most valuable thing that this does because we get it right. And it is stealing some of the package manager functionality. The reason that we do it is because of poor system design. So the system guys created compilers and operating systems that are non-portable without strong interfaces, and so the compiler that you use to build some library has consequences for the usability of that library. You cannot mix compilers most times, and so you have to build everything. So I'm with the eMerge people that everything should be built from source. So that's what it does. It's a package manager where everything is built from source. Now, I think today we can build maybe 60 or 70 different packages. And so you just say download. So I'll give examples. Like here's a bunch of packages that I usually use for finite elements. So I have it build some mesh generators, Triangle and TetGen, and pforest, and some mesh partitioners, Chaco and Medes and Parmedes. And I have it build eigen for small dense linear algebra and pragmatic for parallel load balancing of unstructured meshes, and I use HDF5. I don't usually use Exodus 2, but my friends do, so I'm okay with building it. And we support GMP, we support MPFR for extended precision arithmetic. We try to make it easy to interact with the configure system. So for instance, after your configure, we write you out a script that will, yes?
License restrictions, I saw why you had paramedics there?
Yes. Okay, so the paramedics license is the following. It is, if you want to use this for commercial purposes, you have to talk to me, but anyone using it for academic purposes, it's without restriction. Yeah, George is annoying on that. I don't know why he does it, but so we feel entitled to put it in because you can give a flag. I can't remember. If you do minus help, it will show all the flags, and one of the flags is omit any package with a license problem. And so this is what the Debian people do. They add that flag, and then we throw out every one that has a restrictive license like Hyper or it used to have a restrictive license. It may be BSD now. I'm not sure. They were changing. So, for instance, Trilinos is supposed to have BSD. It's not clear like it's all the way it does right now, but that's, if you talk to Mike, that's the claim. So hopefully all packages transition to BSD type licenses like we have, but the ones that don't have it, we can omit automatically. So we write a script that will reproduce exactly your configure in case you want to reproduce it, like something goes wrong or you can't remember what you did. You can also use that script to easily make a new configuration that's almost like the one you had. So what I usually do is get a configuration that works, debugging, and then I run that reconfigure script, tell it a different architecture name, and I turn off debugging. So this is an easy way to make both a debugging and an optimize that look almost the same. And I usually, when you're developing, I have something like, 20 configurations because we need to test stuff. Does it work with 32-bit integers and 64-bit integers? That's two different configurations. Does it work with complex numbers done in the C style, complex numbers done in the C++ style? Different configurations, and so on. So you can have a bunch of them, and it's fairly easy to manage them because when you do the build, you just have to set this environment variable to whatever. So it's like vpath. It's like vpath builds. So here is a partial list of the packages that we can install for you. If there's a package that we don't install, that you want installed, it is fairly painless to have it installed. We now have a nice modular infrastructure and configure for installing packages. So we have specialized modules in Python that handle make, CMake, and what's another build system? At least those two. And you just drop in the things you want to test, and it's really pretty easy. So a bunch of the new ones have been user developer contributed things. Like people come to us and say, oh, my package is great, here's the install script, and then we put it in and it can now install. That's what happened, for instance, with PETSc. We didn't write it, they wrote it, which was great, because I don't want to maintain it. So you should be able to configure. Hopefully configure runs in a couple of minutes. It takes like 10 minutes on my severely underpowered Air, but it takes 1 minute on like a real workstation, hopefully, maybe 2. It really depends. So the performance of configure is wholly bottlenecked on small file system operations, and that's why if something's wrong with if something's wrong with that, like disk performance was bad on HPFS for Windows, and it could take an hour to configure. So when that was fixed, it went down to a couple minutes. And then the build, thankfully, we've now got, so you've downloaded it from the repository, you configured it, which is just a Python script, and then we build it. The build is the least sophisticated, fastest, nicest part of what happens. You just type make. If you configured with a prefix, you type make install, and it will put it there. You can build, as I said, with multiple configurations. You just change this environment variable. If you don't give it the environment variable, it will build the last configured arch. And there's always a log, and we now put all the logs in arch name, lib, PETSc, conf, logs. So configure.log, make.log, they're all in there. And so we're not polluting the top-level directories with these things. And this is the standard location we understand for logs now. So the make can be done in well under a minute, depending on how many cores you have, because we do make minus j, whatever, you know, and it's
In a really, really clean configuration, like with a bunch of external packages. It takes.
But they're built by the time you make. Make only does PETSc. Configure builds the external packages. That's why that can take an hour. But make, it's a minute. Make for deal 2 can take all day. All day. It's not just get a sandwich. It's like make Thanksgiving dinner long. Yeah. Oh, too bad Wolfgang's not here.
Did you invite him?
I did. I invite him every year. As I said, it's really pretty easy to take a configuration and modify it. So if you decide, oh, everything's working, and I was pretty happy, but then I wanted to go parallel. So I have a running serial thing, I want to go parallel. Now I need a mesh partitioner. I didn't configure with that at first. No problem. You just do the reconfigure, and you say, go ahead and download these things and build them, and it will download, build, link them in, turn on the interfaces in PETSc, and you should just be able to use it. By default now, we build shared libraries, so you shouldn't have to recompile your code at all when this sort of stuff happens. How do you run an example? So we have a lot of tutorial examples. I was talking about deal 2. They're not as well documented as deal 2. That is where they really excel. But there is some documentation at the top of the files. They're numbered, so it would be something like source directory, simplified nonlinear equation solvers, examples, tutorials, and for instance, EX5 is the Bertou equation, the solid fuel ignition problem, or a nonlinear perturbation of Laplace equation. And you type make, and then there's a, you run it directly with MPI run. This is old. We are removing these kind of run targets. We have a beautiful new test system, which I wasn't sure I was going to go into here, but there's a whole manual, a whole chapter in the manual on using the test system, which I think is really nice, but it's kind of more sophisticated than I really want to talk about. So we'll just focus on running them directly. But if you want, the test system is really nice in that you could, for instance, use it to add your own automated tests, and it uses a standard protocol for accepting test results and displaying them and stuff. So it's pretty beautiful, and it's got nice wildcarding for selecting the tests you want to run. So I just want to briefly say, really the only parallel ideas you have to understand to use PETSc are the rudiments of MPI. And the rudiments of MPI you need to understand are basically what is a communicator. A communicator is a parallel scope, much like a variable scope. It's what things are grouped together. So in a communicator, you have a group of processes that are running, and so all PETSc objects have a communicator. What this does is it tells you who's running that object. All PETSc programs are SPMD. Everyone runs the same program that's in the group. If you can split two communicators into two different groups, and then you can create two different solver objects. They will be run as different processes on the different machines. So you can make PETSc code that is MPMD, just by splitting the communicators around and having separate SPMD processes running and then communicate between them. Because MPI has intercommunicator communication. But that's really the only thing you have to understand, because every object is instantiated with a communicator. Another function of communicators is they can cache data. You can give them attributes. You say, well, I want to tell you this thing. So we use that, for instance, to serialize output. We tell the communicator, here's a handle you use if you want to do serial output, and then everyone sends to one guy and he does the output. So I talked about that. You also, from a performance point of view, should understand the difference between point-to-point communication and a reduction. So what's the difference? Point-to-point communication is when one process talks directly to another process, just like it sounds. Reduction is where everyone talks. So what's the difference? Well, if only two guys are talking, the rest of the guys can keep running. Whereas if everyone has to talk, then we've all got to kind of stop and agree. And so there's blocking. So there's a lot more latency associated with a reduction than with point-to-point communication. So sparse matrix multiply has only point-to-point the way we tend to run it. You can actually make it use reductions if you want by command line arguments, but by default it does point-to-point. That tends to perform pretty well. Dot products are reductions and have to be. So when you think about trying to understand the performance of a complicated code at a high level, the first thing we tend to do is go in and look for these representative things. You look at the profiling and you say, okay, how fast is matmult running? How fast is vec.dot running? That gives you an idea what's the latency on the machine look like. In fact, we output separately how much time does it take to do an MPI barrier, just to give us the basic number. But this tells us what's the balance on the machine between memory bandwidth and latency. And then you can look at the difference between like vec m dot to vec dot to see m dot should be limited by bandwidth and vec dot should be limited by latency. So how close they are tells you something about balance too. So if you are building a code for the first time or getting a code for the first time, like one of the examples, and you don't know anything about what's going on, the easiest way to get an idea about what's going on is to view things. And the recent changes that Barry made, I think, make it really easy, much easier than it had been before and much more flexible than it had been before to view things. So let me actually, shoot, this is why I wish I had my machine plugged in now. All right, I'll just tell you. So if you just give view by itself, the default is to output some kind of text representation. So you say vec view, okay, that just prints the vector as text. You know, if you say KSP view, it prints a little description of the solver. Our SNES view, a little description of the solver. And the SNES view will give you a description of the nonlinear solver and also a description of the linear solver. Linear solver gives you a description of the preconditioner, so all the nested objects print out. So you can get an idea what's going on here. But can we do better than that? Yes, because the view takes this it's actually four argument style, and each of the arguments can be default. Now here, all the arguments were default. So what are the arguments? You can change the type, you can change the output file, you can change the mode, and you can change the format. So let's look at what those do. So here, I want to view a sparse matrix. Now, if you just say mat view, it prints out the sparse matrix, which, you know, if it's anything above 4 by 4 is like unreadable, right? So what do you do instead? Well, you can do this. You can say mat view draw. You don't need the colons, actually. I just wanted to show you that you can have other arguments. So if you do mat view draw, it puts up an X window and draws a picture of it, like SPY does in MATLAB. If you say mat view ASCII : ASCII MATLAB, it will print out a MATLAB ASCII file that you can load directly. If you say mat view binary : it will print out a binary that can be loaded by MATLAB. Oh, and you can give the file name here. It's a binary : name of file. You can get a binary file, and we have MATLAB code that can load those automatically. So here I've done it. Oh, I did it. So I'm putting it in a binary, or I'm doing it in MATLAB, or you can output it over a socket. You can change the format. So mat view ASCII info detail, actually it's better DM view. So DM view by default just gives you a little bit of information about the mesh. But ASCII info detail will give you a lot of information about the mesh. So you can control the level of detail that you want in addition. So the way I now structure my code is I don't put specialized code in for output anymore. It's all on the command line. So let me give you an example. So I have a code that I'm writing that does mantle convection simulation, right? So there's a lot of things you might want to output. You might want to output the velocity and the pressure, but you also might want to output the initial thermal structure that you use. You might want to output the derived velocity that you get out of that thermal structure, or viscosity that you get. So how do you organize that? And so what I do is I just put, we have a function, vec_view from options. And so you say vec_view from options, this vector. Vec_view from options, that vector. So I have about 4 lines that everything I might want to output, I put in there. By default, nothing happens. But if it gets, so each one of these, I'll show later, you can, the PETSc input language has 2 operations. One is you have a option, and the second one is you can have a prefix to any option. So you give different prefixes to each one of these vectors, and then you can give something like press vec_view, velocity vec_view, viscosity vec_view. And so if I want to debug, I can output them as ASCII, or I can draw them. But if I want to do checkpointing and stuff, I put pressure vec_view HDF5, name of HDF5 file, ::append. And I can put all of these in the same HDF5 file, and then I can just point pair view at the HDF5 file, and I can look at them. So that works in parallel. It's totally scalable, fairly robust. I mean, it says robust as HDF5, so that gives you an idea. This is now how we do things in Pilot, for instance, and how I would do them for all new development. And I think it's very nice in that it's quiet by default, totally customizable without rebuilding your code or writing any new code, and can do large-scale things. There's also monitoring, and monitoring, so viewing is give me a representation of an object. Monitoring is give me a representation of a process. So the most important processes that we have are solves. So most of the monitors are about solves. So KSP monitor by default will print out the sequence of residuals. KSP monitor true residual will print the preconditioned residual, the true residual, and the norm of the right-hand side initially. You can print stuff about the solution update, about the solution, about the range. The range is a cool one. So you want to look at how many entries have big residual and how many have small residual. If you have a simplified topology, like let's say you have a regular grid, there's a really neat solver that Barry wrote. So imagine you have a regular grid and you look at the range and you say, okay, what's the big residual, what's the small residual? Collect together all the big residuals, because very, very often an extremely small number of cells have big residuals. On the structured grid, we can easily draw halos. So you draw a halo around the big residual guys. You just collect them all up, draw the get the halo, solve that. So subspace projection method works fine, and then project back into the big space and keep going, and it's extremely effective. And if you look at some of the new papers by Xiaoxuan Cai, he's doing this with PETSc for nonlinear problems, which the multiplier is quite a bit bigger. Here, it speeds up a linear solver. There, it makes formally unsolvable nonlinear problems solvable. So this goes by several names, nonlinear elimination, but we call it right nonlinear preconditioning in our paper in SciEM Review. We can also do things like spit out the singular values. So you can also get more help. As I said, the website is there. We have a manual pages. We have a FAQ. We have, really good support at the email list. Or bug other people who know what they're doing, who I've identified here, some of which are in the audience, and love to answer questions. Love to answer PETSc questions. Should put their emails next to their names. So, okay, so that was the intro, and I just wanted to give you a feel for how the package design looks a little bit, what our goals are. And now I was going to go through, suppose you have a code and you want to get PETSc in your code. So I've done an hour, is that right?
Yep.
Okay, so I get one more hour. Does anyone, do you need a 5-minute break, or are you, yeah? Okay, let's do 5 minutes, because I will keep talking, no doubt. Yeah, I'm going to talk while you guys are breaking.
Are you a professor?
Exactly. Yes.
I was going to look into that, but I didn't want to disturb.
Yeah.
Yeah.
That's it. I thought with break it
Yeah.
would be a lot easier to see.
Oh, no, yeah. Yeah. Oh, you think they're on the control panel there?
They are on here.
Ah.